We're going to look at an example involving the growth of a population of bacteria. With population growth examples, the rate of change of the population is proportional to the current population. The population is then equal to P at 0, which is the initial population, times E to the KT, where K is called a relative growth constant. Let's now look at the growth of a population of bacteria. We're told that a bacteria culture initially contains 150 cells and then grows at a rate proportional to its size. After 2 hours, the population has increased to 600 cells. We want to first find an expression for the number of bacteria after T hours. Let's start by letting P equal the number of bacteria at time T. In our problem, we are told that the bacteria culture initially contains 150 cells. So that means that P of 0 is going to be 150 cells. It's always good to put units with it. And then we're told after 2 hours, the population has increased to 600 cells. So that tells us that P at 2 is 600 cells. We are told that the population grows at a rate proportional to its size. That means that the rate of change of the population, dP dt, is equal to some constant K times P. This is a differential equation, and the solution to this equation is P of T is equal to P at 0 times E to the KT. Here's our P that we want to find. P of T contains P at 0 and K. We were already told that P of 0 is 150 cells, and then we can use the fact that P of 2 is equal to 600 to find K. Let's start by just plugging in what P of 0 is. So we have P of T is P of 0, which is 150, times E to the KT. Now we're going to solve for K. Let's plug in that P of 2 is equal to 600. So we have P of 2 is 150, E to the K, and then T now is 2. And this is equal to 600. Let's go ahead and divide both sides of the equation by 150. So we have E to the 2K is equal to 600 divided by 150, which is equal to 4. Now we need to solve for K. We're going to do that by taking the natural log of both sides of the equation. So we have natural log E to the 2K is equal to natural log of 4. We can pull the 2K out in front. That's just a property of logarithms. And then on the right, we still have natural log of 4. Natural log of E is 1. So we have 2K is natural log of 4. And then we can solve for K. And we have that K is 1/2 natural log 4. Now what we're going to do is plug this expression back in for K. And we get P of T is 150 E to the 1/2 ln 4 times T. Now we're just going to change around the variables in the exponent. So we have 150 E to the natural log 4 times T over 2. And we're going to group this part together because that is actually equal to 4. So we have 150 times 4 to the T over 2. Now we're going to go ahead and simplify this, and we'll just flip the 1/2 and the T. So I'm going to write this as 150 times 4 to the 1/2 times t. And then 4 to the 1/2 is just the square root of 4, which is 2. So we get 150 times 2 raised to the t power. And that's our expression for the number of bacteria after t hours. Let's now find the number of bacteria after 4 hours. This is a lot easier. All we have to do is take our expression that we found for P and substitute in that T is equal to 4. So let's write down our expression for P. P of T is 150 times 2 to the T. Now we're going to plug in that T is 4. So this gives us 150 times 2 to the 4th. This is 150 times 16. And when we multiply that out, we get 2,400, and we need to put units with this, and it is in terms of cells. This tells us that after 4 hours, there are 2,400 cells. Let's now look at part C. We are going to find the rate of growth after 4 hours. Whenever you see the word rate, that means that we are going to be taking a derivative. Let's start by writing down what our population is. Our population of our bacteria is P is equal to 150 times 2 to the T. The rate of growth then is dP dt. And that's the derivative with respect to time of our right-hand side, 150 times 2 to the T. Over here on the right, I'm going to write down a formula. The derivative with respect to T of A raised to the T is just A to the T times the natural log of A. Let's now use that formula. So we have dP dt is equal to 150 times 2 to the T times natural log 2. Now we want to find dP dt when T is 4 hours. So dP dt when T is 4 hours is going to be 150 times natural log 2 times 2 raised to the 4th power. When you put this in your calculator, we get an answer of approximately 1,664 cells per hour. This tells us that after 4 hours, our bacteria are increasing at a rate of 1,664 cells per hour. Now let's look at the last part. For this part, we want to find when will the population reach 12,000 cells. Whenever you see the word when, that means we are going to be solving for time t. Our population of bacteria is 150 times 2 to the t, and we want to see when this is going to equal 12,000 cells. So we are going to be solving for t. Let's first go ahead and divide by 150. So we have 2 to the t is 12,000 divided by 150, and that is actually 80. Now to find t, we need to get t out of the exponent, so we're going to take the natural log of both sides. So we have natural log of 2 to the t is natural log of 80. We can pull the t out in front, so we have natural log of 2, and on the right-hand side, we have natural log of 80. Now we're just going to solve for t, and we get that t is natural log of 80, all divided by natural log 2. When you put that in your calculator, you get an answer of approximately 6.32 hours. In 6.32 hours, the population of bacteria will be equal to 12,000 cells. We started with 150 cells, and now after 6 hours, we have 12,000 cells. And that's because the population is growing exponentially.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.